Hello? Yeah. Okay, good. I think there are a lot of interesting talks. I've really enjoyed the event so far. So this is my last talk. I'm happy I'm almost done. So we have we heard a lot of interesting talks and works about NVM and NVMe-SSD or NVMe over Fabric. So we just want to share some of the experience we got during the last 2 years, whatever we worked on the big data stacks with NVM and NVMe-SSD. So as I mentioned in my earlier talks, actually, there are a lot of potential use cases for the big data stacks to utilize NVM or NVMe-SSD with RDMA. If you look at this figure, it looks like no matter you are doing front-end tier in data center business or you do back-end tier analysis, okay, no matter you use key value stores, NoSQL database, or Apache Hadoop or Spark, these kind of frameworks, we see a lot of place or a lot of potential to utilize NVM and NVMe in this kind of scenario. So in this talk, we particularly want to give some examples for the Apache Hadoop case studies. So for some of you may not be familiar about Hadoop, but let me just give you a quick overview of what Hadoop is. So basically, Hadoop is like you can think these days like an ecosystem, not just like one software library. A lot of people trying to contribute different components into Hadoop projects. So the most popular ones like HDFS, which is the distributed file system, and then MapReduce, the default computation engine on top of HDFS, and then Spark, HBase, and then Flink, Extra, those kind of things are available also. So the major target, the major interesting thing we are trying to show in this talk is about NVM and NVMe-SSD. So like many talk already mentioned that this has been available for your purchase and the deployment. So like I mentioned earlier, we have a lot of projects under the HiBD project so that you can get the native RDMA support for big data ecosystem. But most of the performance numbers, whatever we showed earlier, is only for DRAM plus RDMA, okay? So how the numbers will look like for if we use NVRAM and use NVMe-SSD with RDMA. So what happens for those kind of environment? So that's the major question we are going to answer in this talk. Well, some of you know that NVM and NVMe this time is getting momentum, especially from the performance perspective. NVM and NVMe-SSD can give very good latency as well as throughput. And another important thing for NVM is that you're able to get byte addressability so that you can directly access NVM with RDMA operations. So for some of you, if you're still new for the NVM programming, then this picture actually shows you that typically there are 2 ways to use NVM. Here we just show that we are using DRAM to emulate the NVRAM. So, but if you have actual NVRAM, you can directly do these type of things. So like many talk already mentioned, this is your application, okay? You can have a file system on top of your NVRAM device. So then you can actually do the traditional like open read write, those kind of things, like use NVRAM as a block IO device. Or you can also use PMDK, many people mentioned there, persistent memory library, so that you can use that library to malloc or memory copy persistent, those kind of operations to programming with your applications. This is how you can utilize NVRAM in your applications. So in our group, we have been trying to develop a library, a very thin library, high-performance library, so that we can bring this kind of semantics or mechanisms into big data stacks. We don't want to like write, let's say today Hadoop, we write in this way, tomorrow Spark write in other ways, right? So we want to abstract a small library called NRCL, which means NVM-aware RDMA-based communication IO schemes. So basically, if you look at what kind of scenarios in your real application when you do the data transfer for DRAM and NVRAM, they basically have 4 cases, right? You can do DRAM to DRAM communication over RDMA, or you do DRAM to NVRAM, so your source is DRAM, but your destination may be NVRAM. And then you can also have NVRAM to DRAM and then NVRAM to NVRAM. So this is different kind of scenarios. So like typically what we do is, for example, let's say we can use both send and receive semantics as well as RDMA read semantics to implement these type of things. let's say if you're, especially for example, if you have small message, like what we did in the MPI, like eager protocol, we can copy those data into one buffer and then do we send. But the thing is, before we send the acknowledgement, we make sure that this data has been serial flashed to your NVRAM to get persistent. Similarly, for the RDMA pass, we are using RDMA read because RDMA read can make the semantic more clear. Because RDMA write, we heard, right? You need some kind of way to guarantee that data is persistent. You need to RDMA commit those kind of extensions. But for RDMA read, because what we can do is we send RTS, and then we will reserve the NVRAM buffer, and then we use RDMA read to get a buffer. And then when we have these things, we can do a serial flash, make sure that it's done. So with this, we can guarantee that the data is persistent into memory before we send back the thing. So this actually made some numbers we took with PMDK and PCM disk. So we are trying to see that where the performance, what kind of performance numbers we can get. So here, multiple lines. So DRAM to DRAM, of course, that's the very good performance, right? But NVRAM to DRAM, DRAM to NVRAM, NVRAM to NVRAM, and also a different way to do the synchronization of your memory. So what we see is that NVRAM to remote NVRAM, of course, this is the worst case because both sides you need to guarantee the persistency. They're almost 10 times overhead compared with DRAM to DRAM. But DRAM to remote NVRAM around 8x because your destination is the NVRAM, so you have to persist that. But DRAM to NVRAM to DRAM is a little bit better because your source data is in NVRAM already. So this is about send and receive. You can also, like I said, we also support the RDMA read, so that this is similar kind of experiments, but we just did it with the RDMA read protocol. So RDMA read outperforms send and receive based on numbers, whatever we got for large messages. This is also similar to the DRAM to DRAM based RDMA communication. So with these things, now the more interesting I want to present here is actually how to use these things in the big data stacks. So where we actually can use it, and what kind of benefit we can get. So first thing I want to present here is about HDFS. Inside HDFS, why you need NVRAM, why you need where you can use NVRAM, right? So this is how HDFS traditional pipeline protocol. So this is your lame node is client, and the client said I want to write one file into HDFS. So then HDFS will try to replicate your data in 3 nodes in a pipeline fashion. Okay, so here you need to make sure that data actually persistent in a disk traditionally. Okay, or so in persistent domain. So that with this actually we can replace the disk or SSD with NVRAM, right? So that's one of the biggest big opportunity to optimize HDFS. Another thing is, for example, in the traditional RDMA design for HDFS, what you can do is here you do RDMA transfer from DRAM to DRAM, and then you persistent, and then DRAM to DRAM, persistent, DRAM to DRAM, persistent, and come back. With NVRAM, right, you can directly do one traffic. RDMA write to NVRAM is already persistent. So it will save a lot of time of that. That's the reason you can get benefit out of NVRAM. So we actually did some designs. We published in ICS 2016. What we did is, first of all, we bring RDMA to whatever I presented earlier, the RDMA protocol into the NVRAM. And then we support both block access as well as the memory access. Okay, two ways we want to compare the performance. And we also have some hybrid design, how to do the different kind of replication kind of things. And then we also analyze what kind of data, because of the cost of NVRAM, right? We are trying to see what kind of data we want to put in NVRAM, what kind of data we want to put in DRAM or put into the disk something or SSD. So here's some numbers. So what do we see that, of course, the memory IO-based mechanism is much better performance-wise. It shows best performance, for example, compared with the default HDFS or block IO-based HDFS. The performance, the maximum you can get around 4x performance improvement. That's very good benefit. This is for the SDS commit. This is our local cluster, which has full nodes. That's also show like around 4x or 2x performance improvement for read and write. And then you can also run NoSQL database on top of HDFS. Okay, NoSQL database, when you do the query kind of things, sometimes the traffic also go back to the HDFS layer. So for that, we can see around 21% improvement, something like that. Here, we just put the write-ahead log into the NVRAM space. So that's about the HDFS and some application on top of HDFS. Now another interesting part is whether we can utilize NVRAM inside MapReduce engine or Spark engine, whatever MapReduce style computation engines. So this is how one step of MapReduce works, right? You have maps, you have a lot of spills maybe, and then these ones get shuffled over the network to the reduce side. So here, this is the communication operations. And then in the meantime, you probably, some of you may not know that there are a lot of spill operations and the out-of-core merge operations happening inside MapReduce. So this kind of disk operations. So along this phase, definitely NVRAM can be helpful as well. Let me show you some examples. So in default MapReduce, what they did is, so once you've map phase done, you have to flush your data to the intermediate data directory. Typically, this can be SSD or local disk. Now, if you have NVRAM, what you can do is, this is default, still you will go through RDMA, okay? All the operation will be in memory, but in the map side, they still have a lot of I/O operations in the disk. So the question is, can we do with NVRAM? So if you have NVRAM here, instead of flush those data to the disk, you can directly use NVRAM to save those map outputs, right? And then this NVRAM becomes bytes addressable. So later on in the reduce phase, you can directly do RDMA read to get this data from the map phase. So that's where you can utilize NVRAM efficiently in the MapReduce engine. So with this, you can minimize the disk operations in the spill phase, especially. So that's give you a lot of benefits as well. Let me show you some of these numbers. So we run sort and tear sort with different kind of data size. We compare different schemes like default MapReduce over IP over IP and the RDMA-based MapReduce with DRAM. And then the scheme we proposed, NVRAM-aware RDMA in MapReduce. We see very good performance speed up, like 55%. Here, like a map phase, we can reduce like 2.3x. Those kind of benefit you can achieve in the MapReduce. So here we run some high bench workloads, different kind of benchmarks. So maximally, we can also see like 42 or 39 kind of performance improvement, depends on your shuffle data volume or those kind of things. And then there's another benchmark called Puma, which was developed at Purdue University. So the idea is that sometimes your application may have different characteristics. So they want to design some micro benchmark kernel kind of things to capture those kind of application scenario. And also they make some real data sets available. So we actually download their real data sets, we run with their application. So we see almost around 40% improvement, 50% improvement for different cases as well. So whatever I present is about NVRAM. So actually, NVRAM and the NVMe-SSD is different. Okay, even for Intel, right? You have PMDK, you have SPDK. So if you want to play with NVRAM, you should use PMDK. If you want to play with NVMe-SSD, you should use SPDK. So I think many of you, your talk already mentioned about the NVMe standard. So NVMe standard, this picture actually shows the steps, how you typically save, read and write your data from the NVMe device. Actually, NVMe standard is pretty much similar to RDMA concepts, okay? So just like Liran already mentioned in one of his tables, right? You can exactly map some NVM queues, those kind of things with RDMA verbs. So this is the steps I don't want to repeat. So, but NVMe is not something I want to highlight here. Actually, I want to highlight NVMe Fabric because this make big data stacks. This scheme is really useful for big data stacks. Just like what I mentioned earlier, like HDFS. If you can do this, you can directly bypass CPU, right? That's very good. So for example, this is your host. Think about this your application. And then this is your data node. If you can directly use NVMe over Fabric protocols, including if you can offload it to NIC, you can directly get a much better latency and high throughput because you can offload to here, and then this NIC will take care of it. And if this NVMe target, like Lina also mentioned, if this one can be offloaded, and this staging buffer can also be offloaded, all the things will be very efficient, I believe. Okay. So, but there's a lot of challenges as well. Okay. So here we just show some kind of co-design opportunities from our understanding. So there's multiple perspectives. Performance is one of them, of course. We hope to get the best performance as much as possible out of the NVMe protocol. Some other perspectives are also important, like a QoS. If some of you familiar with NVMe standard, there's a lot of actually words about how to achieve QoS inside NVMe. We actually want to show some of those results as well. On the virtualization, because I think the standard also mentioned about how to support SRV, and all the things can benefit new software ecosystems like disaggregated storages with NVMe over Fabric and the persistent caches and the database, all those kind of things. So here, like I think today, Intel SPDK guy mentioned, RocksDB already support NVMe design. So we actually evaluated with it in our local environment. So what we see that for the insert or write sync, we tested with insert, write sync, and read write, this kind of benchmarks. We see 20 or 33, 61% improvement. That's pretty good. But for overwrite, we see that SPDK actually, there's a little bit of performance overhead compared with POSIX. And for read, somehow there's some kind of overhead as well. So we're trying to do additional tuning and optimization in the future. But overall, I think the number looks pretty good with RocksDB. That was latency. And then this with throughput. Similarly, for this one, it's good. Insert higher is better. And for write sync and read write is also better. So, but for overwrite and random read, there's some kind of overhead existed. So that's about performance. Now, another thing is about the QoS. So basically, here the idea is that in NVMe standard, they provide some kind of QoS definition. So you can implement some kind of arbitration logic in the NVMe hardware level. Okay. So the default one is like a weighted round robin. You can implement that over there so that you can say, okay, what kind of bandwidth throughput this application should achieve, and the other application may be lower, depends on the QoS setting, right? So we actually did some experiments. Let me first introduce the scenario one. Actually, I should show this figure left and this figure right. Okay, scenario one basically, let's take a look this green one and the yellow one. So this is actually the default. We follow the default WR, weighted round robin scheme. We see that actually the QoS is not guaranteed at all for some reason. I mean, we tried a lot of cases. No matter different scenario basically means whether you set a high priority, medium priority, or low priority, or mix those in different way. So the WR is not that much. Is not very good actually. So we propose some kind of another design schemes, which actually can guarantee that. For example, this is with our design. We can show that if you set high priority for your application, we can get around 100 megabytes per second. In the meantime, if you say that this one is a median priority, then you only get 50. So the ratio is exactly matched with user settings. And we also test with many other cases, like 2, 3, 4, 5. Similarly, with default WR, we don't see very good. The gray bar means the desired ideal QoS support. But the actual one is not that good, okay? But the yellow one, whatever we proposed, can exactly match with the desired QoS support. So which basically means that not only performance, you can also think many other things to do with NVMe standard, for example, QoS. We believe that this is also very important for real cloud environment, right? You are not just going to show that, okay, your performance is good. You need to also show that with multi-tenant environment, you should guarantee that, okay, this tenant should get the desired QoS support they want. Okay, so with this, let me conclude our talk here. Basically, in this talk, we are trying to exploring NVM-aware RDMA-based communication I/O schemes, especially for big data analytic stacks. So we proposed a new library and RCAO, which is work in progress. We showed some kind of redesign in the HDFS layer, as well as in MapReduce layer, how to utilize NVRAM in what kind of why and in where, okay? And in what kind of fashion you can utilize that and get a good performance. And in the meantime, we also discussed something about how to design the big data stacks with NVMe and NVMe over Fabric protocol. So all these numbers, I think, is promising, and we actually have a lot of interest to try the NVMe over Fabric offloading those kind of mechanisms in the future. And we also try to co-design with more stacks. Like I mentioned yesterday, we have exciting workshop. We are trying to discuss these kind of things with academia guys as well as industry guys. So with this, let me thank you. If you have any questions, I'm happy to take them.
Can you bring up slide 15 again?
Slide 15?
Mm-hmm. No, it's not 15, it's 20.
Okay.
Yeah, this one. Do I understand correctly that you are not, your proposed work or your work is not changing the current architecture of Spark and Hadoop, MapReduce?
So for this design, we don't change anything in Spark and HBase. Okay. For this design. For this design, we don't change HDFS.
Yeah.
Okay.
Okay. Do you plan to feedback your work to the open source world so that it becomes included into?
Yes. So that one we have discussed that multiple times. Eventually, I think we probably will work with the open source community, see whether they're willing to try these kind of things. But what we see that for big data community, they're still lag behind on the advanced hardwares. So, for example, even not too much of them has this kind of device yet. So
yeah, I'm asking that because we had the same issue with Grail. So we decided that we are starting our own Apache project.
Yes.
And try to cooperate with what is there and not trying to go into Spark and make changes within Spark, but to have a framework which helps Spark.
Yeah. I agree with that.
So that looks similar to me. That you trying to keep it outside and solid. Yeah,
this can work similar to your Cray work, but the only thing is your Cray work is kind of like another distributed file system. You can think like that. But what we did is kind of inside HDFS. So we don't change HDFS API.
Yeah.
We still keep HDFS most of their mechanisms intact and architecture intact. Yeah. So we don't do big changes in HDFS. So we just want to bring our stuff into their ecosystem. Yeah.
Okay. We of course with Grail have an HDFS API as well, so we can also export HDFS.
Okay, that's cool.
If you want.
Yeah.
Okay. Thank you.
Okay. So, but I just want to add another comment on that. Actually, we feel, at least my personal feeling is that maybe NVMe over NVMe-SSD maybe the next step for big data guys. But that's my feeling because NVRAM may be still a little bit far for them. But database guys may think differently. Okay. Good. Thank you, guys.